Lesson 8. So further applications, so the application sections, the units we usually typically have, using sine law and cosine law. So a couple things to review just to make sure that we're aware of. If you haven't figured this out yet, I think actually I've said this to you a couple times, Brett, so you're probably tired of hearing me saying it. SOHCAHTOA and sine, cos, and all those things are only for right triangles. Okay, so that has to, you have to have a hypotenuse, right? You have to have a leg and that kind of stuff. That means you have to have a 90-degree angle. Now, non-right triangles, that's when we're using our cosine and sine laws to solve. Okay, so if we're doing the differences, that's the case. Okay, cosine law we're going to use side, 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 or side angle, side. Sine law we use all other cases. Okay, so sine law we use SSA, right? The ambiguous case. We have to check to make sure we're expecting 2, 1, or no answers. Okay, so that's from our last thing we talked about. Okay, so there's many practical examples this we can go through. We're going to talk about a couple things before we do that. Just some little bit circle vocab to make sure you know what it's talking about. So A, the perpendicular from the center of a circle to a chord does what to the chord? So what that means is if you draw a line that's perpendicular to a chord is a line across a circle that's not your diameter. Okay, so they just call those chords. So if you draw from your center perpendicular to that chord, what does it look like it's doing? Well, perpendicular is 90, that is correct. But what's it doing to the chord? Yeah, bisecting. It's cutting it in half. Now, that's not just for this location. That works for all chords, and I'll show you what I mean. If I drew a chord, I said a chord's a line through the circle, right? So if I drew a line through the circle, yep, we talked about this a little bit in grade 9, that chapter 10, that last section. Okay, now if I draw it right here, perpendicular, let's see here, perpendicular looks like it's right about here. Look at that, it's pretty much right in half. Okay, it's not a coincidence, it happens every time. Okay, so this is bisects. All right, the measure of the central angle is equal to blank, the measure of the inscribed angle. Okay, so we're talking about, remember the relationship, this is also from Math 9, like Witzke said, so these are inscribed. So inscribed are just angles that are across the circle. Center is coming from the center. And so what's the relationship of YZ to X? Well, yeah, but that's true in this case, but the quick thing is the central angle is twice the value of these ones. So like this is 60, these would be 30s. Okay, so central angle is twice as big as an inscribed angle. Now, no matter where, it's about where they finish. See how they all finish at CA? That's what causes them to... Right. Yeah, I can do a T point here. As long as I'm going to C and A, these angles are going to be the same, which is going to be half of that one. Yeah. So this right here we put twice. It says measure of the central angle is equal to twice the measure of the inscribed angle. Subtended. Subtended means they're sharing the same arc. What arc are we talking about here? CA. That's subtended CA. Okay. The inscribed angles subtended by the same arc are equal. So this S is equal, so Y and Z are equal, or Z, and then the one I made is also equal. So these three angles are all the same. Okay, so this is equal. Okay, tangent to a circle is blank to the radius at the point of tangency. So tangent, we actually know what that means. We talked about before. That means it hits the circle at one spot. And if you draw the radius down and connect that spot, it forms a perpendicular angle. Okay. So we just need these definitions to help us solve when we're doing a couple of these things later today. Again, these should be review. Okay. All right. Let's keep going here. All right. In the diagram, O is the center of the circle, radius 3.25. QR equals 2.5. RS equals 4.7. Calculate the nearest whole number, the length of PQ. So let's label the stuff we're given first. O is the center circle has a radius 3.25. So we know O is the center, so we know the radius is 3.25. So like half that line there. We know that QR is 2.5. So I'll just draw an arrow here so it's a little bit spaced out. That's 2.5. And then RS is 4.7. Okay. So we're trying to find PQ. Okay. Trying to find PQ. Now, there's one other definition here that's happening right now that they should have revisited. Not quite. See what is PR really? See PR all the way across? What is that? Right, it's 6.5 and it's the diameter, right? Now, there was a thing we talked about in Math 9 and your older math classes. If you have a diameter here, if I put a dot anywhere in this circle and I connect them, what's that degree going to be? Yeah, it's 90. So if I put a dot here, every time that's going to be a 90-degree angle because QPR. Oh, yeah, to find sine. Yeah, you could. So two things that, let me slow down here. So the first thing I just wanted you to recognize is that by definition, guys, Q is a 90 degree. Okay, Q is a 90 degree by definition. However, if we want to go with what he said, which is fine as well, is that so we just want to use Pythagorean theorem. So yeah, so that's 90. Right, 6.5 like Joel said, so we just want to use Pythagorean theorem actually, that's all we want to do. So it's 2.5 squared plus, we're trying to find PQ, equals 6.5 squared. And we can do that because we figured out that's a right triangle. Okay. So when you solve for PQ here, you're going to do 6.5 squared minus 2.5 squared. When you do that, you're going to get 36 equals PQ squared. And so PQ is 6. Okay, so this right here is 6. Okay, now I want to find the measure of QPR. So QPR we can do now, but we have to use, we can simply, since it's a right triangle, we can use our trig ratios. Okay, so we're trying to find QPR. We're trying to find this angle here. We can use any trig ratio we want, right? Because we have the opposite, the adjacent, and the hypotenuse. So we can use any one we want. Okay, I'll just use sine. So what is the opposite side from angle P? 2.5, right? What's the hypotenuse? 6.5. So it's sine of the degree of the angle, so theta, equals 2.5 over 6.5. And then what do we do to get the degree? What's that move we do to solve for theta? Inverse sine. So you're going to do inverse sine of 2.5 over 6.5. And that will equal theta, which will give you the degree measure. Should get 23. Make sure you're in degree mode. Okay. And then it wants the angle of SQR. So a couple things. SQR. So we're trying to find this sliver here, that angle. So it's a piece of the 90. How can we do that? So we're trying to find SQR, so this sliver right here, like that's making that angle right there. Right. Right. What's what we need? So Botsky just told us the part that we actually need. We have two sides of this triangle. It's hard to picture because I've drawn all over it, but right now we're looking at this triangle for that last part. We have two sides of it, right? We'd like to have three pieces of information. Well, like Nolan just said, this angle that we just found is equal to this angle, right? Because they go to the same subtended arc. So here, those are inscribed angles. So we can go ahead and write that angle S is 23. Okay, angle S is 23 because angle P is. Now, one question. The triangle outlined in red, is that a right triangle? Yes or no? No. So we're off the SOHCAHTOA train. We can't do that anymore. Okay? So we're back to sine law, cosine law. Do I have a comparison? Yes or no? Yes. So we're using sine law. My comparison is 23 makes 2.5. So now I want to know what makes 4.7. Okay, so you would write it as sine of 23 over 2.5 equals sine of the unknown q over 4.7, and then we solve. We multiply by 4.7, and we inverse sine that answer. When you do that, angle Q, or SQR, same thing, is 47 degrees. Okay, does anybody have any problems using the inverse or anything? Okay, so that was just kind of like the straightforward stuff. Now we're going to be kind of talking about bearing and direction. Okay, so no questions? All right. Okay, we're talking about bearings, and then we're going to talk about the alternate way, which is, it's just another way of saying direction. But so it's like mapping or making a grid or stuff like that. So bearing, so what does bearing mean? When it says bearing, the bearing of one point from a second point is a way of giving the direction. So the diagram shows 2 points A and B, and the north-south line through A. So what that means is that north-south, okay, that's your north-south, that's your east-west. Okay, the bearing from B from A is the measure of 125. So you're always going to go from north in the clockwise direction. So if I said you're bearing 125 degrees, that means you go 125 degrees clockwise from north. So here's north, right? So essentially the y-axis. I'm going to go 125. So there's the 90, right? And then the other, what's that, 35? Okay. And so this one's pretty straightforward with that. So if we want to label these, this one would be what? Bearing 60, right? 60 degrees from north, 240 from north, 340 from north. Okay. All right, so let's kind of talk about a couple things here for an example. All right, a liner leaves at a port P, so we're right here to start, port P. Sails 15 kilometers on a course of 37 degrees. Okay, so this is the tricky part. 37 degrees is not this angle, right? It's 37 degrees if I drew the altitude line. This is 37 because it's from north. So it's 37 degrees like that. Okay, and that's 15, he went 15 kilometers. So I'm just labeling the information they gave me. To position Q, where he changes course to 70. So he's sitting here at Q after 15. So here's my north line, and he goes 270. So he goes 90, 180, 270. So essentially he went perpendicular, right? He took a hard left. Okay, so there's your 270. So if he went 270 there, we'll use that to kind of help us figure this out eventually. Okay, but we can't figure out what that is yet. We'll talk about that in a second. All right, and then the last part, he sails 12 kilometers to R, so this is 12. Complete the sketch to illustrate this information and calculate the distance and the course the liner must sail to go to R to P. So we're trying to figure out what this distance is. Okay. All right, so angle RQP, how can we figure out what RQP is? Well, guys, we know, what's that? Actually, we don't have to because you know we went straight up. This is perpendicular. So we have a right triangle here. 37, we don't know what 37 makes in terms of a side. Oh, wait, no, you're right. We can use cosine law. Yeah, you're right. Right. Yeah, we're actually, because the 12, we don't know what this is broken up into. Yeah. Okay, so we're going to do triangle PQR. So what we have is that PQR, let's go ahead and look at this real quick here. All right. All right, hold on here 1 second. So, and we need that because once we get this angle, we have side, angle, side. And side, angle, side is our cosine law. That's what you said. So yeah, simply that was just an oversight by me. Let's redraw that. Whoops, don't want to redraw all of it, but it's okay. So we have our first thing, 37. That makes a perpendicular there. This whole thing's 12. We got here, they did a 270 rotation. Okay, and then this was 15. Okay, so the first thing we did is we go 90 plus 37. We subtract that from 180 to get the other corner, which is 53. So we're at 53 right here. And now that we've done that, to help us with PQR, because remember, the goal is they want to know what RP is. So we're trying to find out side RP. That is cosine law because we have side, angle, side now. We have side, angle, side. So you're going to go 15 squared plus 12 squared minus 2 times 15 times 12 cos 53. And then you can calculate this and square root it. So when you do that calculation on the right, you should get, we're calling this side Q because it's away from Q. Q squared is 152.3. We square root, Q ends up being 12.34. So this length is 12.34. Okay. So a couple things they just said. Okay, they just said they want us to find the distance. So we found the distance, but they also want us to find the course. So what did he turn? So we're trying to figure out the way he turned to get to position P. How do we do that? Yeah, so it's 9 on that side, yeah. So yep. So what he's saying is we know 53 made what? It made that. Yep, and so then we're going to use this to figure out what that angle is. But with that angle, that's not going to be our full move yet. Okay, what I mean by that is that's not its course, right? Because he started north. So he started north, it's 90 plus this. Does that make sense? Because this is perpendicular, so 90 plus that. Okay, so what Lucas says, right, we'll use sine law here. So sine law, it's going to be sine of 53 makes 12.34. We want to know what sine of, what's that, r? Sine of r makes 15. Solve for r. Okay, when we do that, we get sine of r ends up being 0.9707. Right, and so we inverse sine of that, and it's 76. So it's 76 degrees is this sliver plus the 90. So his turn was 166. His bearing was 166 to get down there to P. Okay, so 12.34 was the distance he went, and he did a 166 turn. So almost 180, almost straight down south, but not quite. Okay, one more of these, and then we'll talk about the other way describing direction, and then we'll do that example as well. All right, so two aircrafts, A and B, leave the airport at the same time. A flies at a course of 90 at 700 kilometers an hour, and B flies at a course of 290 at 600 kilometers an hour. Calculate their distance apart after 12 minutes. Okay, so first off, we do need to figure out the course of which they're leaving a airport. Yeah, what's that? So he's just going straight out, exactly. So this flies course of 90 is going straight out. Okay, the other one flies on a course of 290, so that's almost straight to almost straight to left, but a little bit up. Because 270 is straight left, right? So then 290 is just a little bit more. So this is what it would be, like that. So what I'm saying is this right here is like a 20-degree angle, just so you know. Yeah. Still from north. Okay? But we don't care about how fast they're going. We want lengths. So they tell us 12 minutes and how fast they're going, so we have to do a quick conversion of figuring out how far they went. So 12 over 60, right, because 12 minutes, an hour. Why am I doing that? Because my speed's in what? Kilometers an hour. So essentially, I want to figure out how much of an hour do we fly. Well, how much of an hour do we fly? We flew 2/10 or 1/5 of an hour. So if we went 1/5 an hour, that means they traveled 1/5 of 700 and 1/5 of 600. Okay, so you divide 700 by 6, or sorry, 700 by 5 and 600 by 5. So when you do that, their distance they went is 140 kilometers and then 120 kilometers is how far they went. All right. We're trying to figure out their distance apart. So you kind of see the triangle come into play now. They're trying to figure out this distance here. So which law, or how can we do that? Okay, you guys see that? Lucas said it. We know this. You might have. This whole turn, okay, is 20 plus something is 180. That something is 160. This has to be 160. So that means if it's 160, that's really obtuse. Your other corner angles are going to be super small, right? Okay, so now you have SAS. That's cosine law. Okay, so we're going to go for, we're going to call this side A because it's from airport. Okay, so A squared equals 120 squared plus 140 squared minus 2 times 120, 140 cos 160. That means that A squared is 65,573.67 square root 256. So 256 apart. A couple things to point out. Is 256 much bigger than 120 and 140? It is, and it should be because it comes from the biggest angle. We know that distance apart they are is bigger than the sides, okay? Because 120 and 140 are coming from smaller angles because 160 is a lot of your 180. Okay, and that's it for that one. Just that one, yeah. So 256 kilometers. All right. The other way, which some people actually like this one a little bit better because it's more specific, to do it is they tell you directional. So describing direction. So what they say is, they say there are other ways describing course of A bearing is 125 is the same as 55 east of south. So that means is you go down to south and you kick over 55 east. So you actually are doing south and then I'm going in the east direction. So south 55 east. So like this one right here is north 60 degrees east. This one is south 60 degrees west, north 20 degrees west. So just telling you which way to go and how far. Now, if I wanted the rotation angle, like you know this one right here, south 60 degrees west, that's 180 plus 60. This would be 240 bearing if you wanted the other way. Okay, there's not a right or wrong way, just another way of doing it. We'll do one problem with this one. This problem is harder. That doesn't mean that this one's hard to draw. That's why I've had trouble with it in the past. My point is that it doesn't matter. Yeah, like, right. So like, if you like the original way, then you need to make this right here that way. Does that make sense? Yeah. So if I tell you 50 degrees west of north, for you or like for me, it doesn't matter. Yeah. You can alter the information so it's the way you like. Yeah. All right. So a ship observer observes a lighthouse 50 degrees west of north. Okay, so if we just, maybe while we're practicing here, let's just think about that. 50 degrees west of north. That's here, yeah? 50. We're going to the west. Okay. After sailing 36 kilometers in a direction of 35 degrees west of south, I'm just drawing these directions and we'll apply them to a picture here in a second. So he sails 35 degrees west of south. So that would be here. That's 35 degrees west of south. Okay. Then he observes the same lighthouse from his same that new location, and it's now 15 degrees east of north. So essentially what's happened is he viewed the lighthouse from the bank, and he sailed down a little bit, and now he's turned and he's seeing it at a different perspective. That's what's happening. Okay? So let me draw what's happening. We have the ship's position 1, so we'll call it S1. He's right here. And then he observes the lighthouse at the 50 degrees west of north, so like right here. So like here's the lighthouse to him. Right, he just sees it, and he's going away from it. So he goes this way, south of west. He sails down here. Say that again. 35 degrees. And so now, yeah, and then he spots it, like you're saying. So he spots it 15 degrees east of north. So that means he is past it a little bit. So I need to draw that a little better. So here's the lighthouse. Barely, but yeah, okay. So yeah, so then he east of north. East of north would be like this. So then he's viewing it like this. Right? Right. So like this little thing right here is 15 degrees. Okay. All right, so 15. All right, so what we got to do is try to piece this together the best we can here. A couple of things you can figure out. We can figure out if this is 50 and this is 35, we can figure out what this is, right? Because they're down the north-south line. So this right here is 95, because I subtract from 180. So this is where you got to use parallel lines, and it gets really messy. But so if I draw like the north line through the lighthouse, which this is also a north line here, and this is also a north line here. Do you guys remember anything about like when you have stuff like this, the relationship of like this angle and this angle? Right, like the alternate interior. So you have to kind of think about that as well. So see this 50 here? This line is going through the two parallels. So this is 50 and this is 50. You guys see that? I'll probably give you more information. What's that? Good question. I'm talking about just this piece here. So like the 15's right here, remember? It's past. Which way is east? Yeah, to the right. Yes, he's going, but see, like, this is the north line. This is him going 15 east. Is that what you mean? So like that little sliver is 15. Right. Yeah. Sorry, there's a north line here. Oh, I see what you're saying. Yes, north line. Yeah. Okay. Okay, I see what you're saying. Correct. So, okay, you're actually saying it perfect. So, see how what I was saying is, and this is why this is so hard to draw, and I apologize. So, What's you've actually brought me exactly what I was trying to say, because that 50 doesn't go here. 50 goes here, but it's 50 plus 15. That's what Nolan's saying. So it's the 50 plus the 15. So this is a 65. The part that's hard to see is like we're trying to make this a triangle. That's the part that's hard to see. So that's 65 for this whole angle. So 15 plus that 50 from the parallel line. The reason that's helpful is because now we can figure out this whole angle. Okay, which is 20 when you add them up, subtract from 180. 65 plus 95 is 160, and then 20. Okay, that's why we're doing all that, to get those angles. Okay. Right, and now we can use sine law because we know, so he traveled, I need to label these here, so he traveled 36 here, and then he traveled, that's the only one we know, yeah. So he traveled 36, so now we know 65 makes 36. So we can figure out what 95 makes. Because it wants to know how far he is from the lighthouse. So here, we're trying to figure out this location here. Okay, so sine law, 36 was made from the sine of 65. So what is the lighthouse distance now from the boat with a sine of 95? So we're expecting it to be bigger, right? If 65 makes 36, 95 is going to make something bigger than 36. Oh, excuse me. So you times 95 over, and that's just your answer. You get 39.57. And 40 kilometers if you round the nearest kilometer. Okay. All right, that's it for this one. And then.